So these are the videos that you're going to use to work on the 2 lessons that you'll miss with me. This is what you're going to work on in class if you have a proctor. If you do not have a proctor, please be sure to watch these videos. It's very important. So this is day 4. This is for January 30th. We'll start with slide 25 on Canvas. Basically what I'm going to check for your homework when I get back is that you've completed these slides. So you have this packet, right? And you're going to write things that I write on this packet. You're going to write it in your packet. If you don't have the packet, that's fine. If you were absent when I handed out the packet, you can take notes like you would regularly take notes with the slides. So this is slide 25. Today we're talking about applications of arc length, area of a sector, and particle motion. So remember, arc length is just if you have an angle and you have an arc, right? Remember, Sal used that fancy word subtends, right? Here's theta. This is your arc length, right? So arc length is right there. This is your radius and your angle is right there. Area of a sector, that just means, like, let's say that we wanted to find the area of this shape. Right? If we wanted to find the area of this shape, that's called finding the area of the sector. Particle motion is something else. Particle motion essentially is something that rotates around in a circular motion. So like a fan, right? Or a planet as it orbits the sun, right? Except our particle motion, we're going to be talking about a perfectly circular orbit rather than an elliptical orbit. So that's what particle motion means. Just an object that's a particle, right? That's your object that's rotating in a circular pattern around a particular object in the middle. Okay, so that's just an introduction to what we're going to be doing with applications today. So first, let's talk about expressing decimal degrees versus degrees, minutes, and seconds. So it says express 14 degrees, 36 minutes, and 54 seconds in decimal degrees. So that stuff that I just read right there, that might sound a little bit confusing to you. So I'm going to break it down a little bit. So 14 degrees, right? We talk about degrees, even though we haven't in a while because we've been talking about radians, is something pretty subjective, right? So 14 degrees basically just matches up with our protractor here, right? If I was drawing an angle of 14 degrees, I would just go up to 10 and then count 4 more. 1, 2, 3, 4. And if I draw a line that connects this point right here with this over here, use straight edge. So that forms your angle, right? Now I just drew a 15-degree angle, right? So I'm a little bit off. This is a 15-degree angle. But essentially this is going to be close to that. Now these other numbers are like decimals, right? They're parts of a degree. What's important to remember is that this symbol right here, that means minutes, okay? And it's really helpful that it's called minutes because there are 60 minutes in 1 degree. Okay, so it's just like breaking down an hour into 60 minutes. We can take this little distance between these 2 lines right here and break it up into 60 even little pieces, and that gives us 60 minutes. So we can start talking about decimal degrees. So to convert 36 minutes into degrees, well, we have to divide it by 60. Right? Because 36 out of 60 will give us the decimal version of our degree. So essentially we have 14 degrees plus 36 over 60 degrees. Now this last piece, 54, and then these 2 marks, that stands for seconds. And again, it's going to be nice and easy to remember how many seconds are in a degree because it's the same number of seconds in an hour, which is going to be 60 times 60. So there are 3,000 600 seconds in 1 degree. Right? That's how many seconds are in an hour. So that's how many seconds are in a degree. So essentially we have 54 over 3600 degrees. And then we just convert each of these into decimals and then just add it on with 14. So I wanted to zoom in a little bit just in case you can't read my writing. So again, 36 minutes to convert that to degrees, I would need to divide that by 60, right? That's going to be the fraction, or sorry, the decimal of how many degrees we have. To turn seconds into degrees, we need to divide it by 3,600. So I'm going to bring in my calculator. We have, right now the screen kind of looks funny, but let's see how it looks. So 36 divided by 60, that's going to be 0.6. I'm going to just move that off to the side because it doesn't really show up nicely on there anyways. So we have 14 plus 0.6. And then lastly, we have 54 divided by 3,600, which gives us 0.015. So that means if we have an angle that measures 14 degrees and a little bit more, so 36 minutes and 54 seconds, that means that the degree measurement in decimal form is 14.615 degrees, right? So that's more than 14 and a half. So I still drew that wrong because I kind of drew it as more of a 15-degree angle, but you can see that it would be somewhere really close to that 15-degree line I drew. All right, so then we have to be able to move backwards. We have to be able to take this decimal here and turn it back into minutes and seconds. So right here it says express 72.568 in degrees, minutes, seconds. Well, degrees are nice and easy because we already have the degrees right there, right? So we have 72 degrees. For our minutes, now instead of multiplying, we're going to instead of dividing, we're actually going to multiply. But we need to start with the seconds first. So we're going to take our decimal, or I'm sorry, we're going to go with minutes first. I don't know why I went in the wrong order. So we're going to take our minutes, or to find our minutes, we're going to take our decimal of 0.568, and instead of dividing it by 60 this time, we're going to multiply it by 60. And that's going to give us how many minutes we have, right? So we'll take 0.568, multiply that by 60. That gives us 34 and some change, right? Minutes. Now to show minutes, I'm going to draw that one little line right there. So that means we still have leftovers, right? So the actual minutes that we have are 34. So far we have 72 degrees, 34 minutes. Now to figure out how many seconds I have, I'm going to take this 0.08. Key thing here to remember is that essentially we have 0.08 minutes. Now you might be thinking, okay, well then I'm just going to have to multiply this by 3,600 to figure out the seconds. Well, that's incorrect because this is now in minutes, right? So if we want to figure out how many seconds this is, right, we have minutes to seconds. We should know, or we should infer, right, based on what we have up here, that 1 minute is made up of 60 seconds. So we're just going to multiply this by 60. So 0.08 times 60 gives us 4.8. And we can leave, it says to the nearest second, so 4.8. So 4.8 seconds. So to the nearest second, that would be about 5. So how we would write this right here, 72.568 degrees is equal to 72 degrees, 34 minutes, and about 5 seconds. Okay? That's how you describe really, really small angles. Now you might think, well, why do we need to be able to do that? Well, this is if we're trying to find angles that are covering a large space, like a map, right? If you have a map, something like 72 degrees, 34 minutes, and 5 seconds, right? Could tell you the difference between one house next to another house, or maybe a city next to another city, right? So these are definitely where when we have degrees, we want to be able to break it down into smaller chunks. So that last video was just a little bit of information so that you're able to talk about breaking up angles into smaller chunks. So the warm-up for today's lesson, it says the two legs of a right triangle measure 2 feet and 4 feet. Okay, so those are the legs and they form a right triangle. So 2, 4, they form a right triangle. Find the measure of the hypotenuse, right? That's this guy, in simplest radical form. Then round to the nearest tenth. So we are going to do some rounding. All right, so we have a right triangle, which means we can use the Pythagorean theorem. A squared plus b squared equals c squared. So 2 squared plus 4 squared equals, in this case, we're talking about the hypotenuse, so we're going to call it h. Just because that's what I called it over here. We could have labeled this as c, and that would be fine. 4 plus 16 is equal to h squared. 20 is equal to h squared. Haha, here comes what we learned earlier, right? Simplest radical form is so that we can now work with radicals that aren't perfect squares, right? So the square root of 4, square root of 5. So our answer in simplest radical form would be 2 radical 5. And we're talking about feet. So our answer would be 2 radical 5 feet. And then it says round to the nearest tenth. So what I can do on my calculator, and I'll show you this even though it's going to look funny, is 2 times radical 5. Find out what that is. To the nearest tenth, that would be 4.5. So this equals approximately 4.5 feet. Right, so I'm going to label that up here as well, 4.5 feet. That's my hypotenuse. Probably shouldn't have used h because usually that represents height. So probably use c in the future. Okay, for number 2, a car can drive 117 pi miles. Now that's weird, right? No one usually talks about the distance of something in terms of pi, right? But you're going to be having to use pi in problems with the applications today. So I just want to make sure that you're comfortable with this. So a car can drive 117 pi miles. Well, that's its distance, right? In 6.5 hours. So that's its time. It says, what is the car's speed per hour in terms of pi? So our answer, very nicely, is going to be left in terms of pi. So we don't have to use 3.14. So our speed is going to equal our distance over our time. Our distance is 117 pi, which if you check on your calculator, 117 times pi is approximately 367.6 miles. Okay, you're going to do that in 6.5 hours. So we're going to leave this answer in terms of pi. So if we take 117 and divide it by 6.5, we'll get 18, right? So 117 divided by 6.5 is 18. We're left with pi in there. So our answer is going to be 18 pi. These were miles. These are hours. So our answer is going to be 18 pi miles per hour, or you could write MPH, which I know sounds weird, right? 18 pi miles per hour, but if you multiplied 18 by pi, you would get approximately, right? So it says round to the nearest mile per hour, that should say. You would get approximately 56.5, so that's 57 miles per hour. So 2 parts to that one. Just a quick refresher, right? We saw this when we talked about arc length in general, right? Arc length, remember, is always going to be S. Always. Area of a sector, right? So our area of our sector is going to be this shaded region right here. So here are some formulas, right? This formula, our arc length, is equal to r times theta. And essentially, what we did to find this is we took a formula we already knew, right? We already knew that theta was always equal to your arc length over r. So we just rewrote S with it, what's the word I'm looking for? isolated. Sorry. So when we want to isolate s, right, we would just multiply both sides by r. So r theta is equal to s. So that's where this comes from. So your arc length is always equal to your radius times the radian measure, right? This has to be in radians of your angle. Area of a sector is always going to equal 1/2 the radius squared times your angle in radians. Okay, the formula does not work if it's in degrees. And you can also write this, the area formula, as 1/2 radius times the arc length, if you know it. Right? Sometimes you know the arc length, sometimes you know your angle. So it depends on what you're given, on which formula you're going to use for this particular problem, or problems for arc length and area of a sector. Moving on to example 1, it says a circle track, I guess I should say circular track, has a radius of 27 meters. So what we're going to do is we're going to draw a picture. A person who walks partway, I'm going to zoom in a little bit so you can see a little bit better. A person who walks partway around the track forms an arc. Find the length of the arc intercepted if the central angle formed is 160 degrees, right? So I know you guys don't like working with radians, so here you go. Unfortunately, in order to find the answer, we need to work with radians. So we're going to have to do some conversions first. But 160 degrees, right, is not quite 180. So our angle of 160 degrees will look something like that, right? So we're supposed to find the length of the arc intercepted if the central angle is 160 degrees. So the central angle is 160 degrees. So our theta is equal to 160 degrees, but we're going to need to write that in radians. And then what the question is asking for is how long is this distance that has been traveled along the outside, and we call that the arc length, right? And we also have our radius here is 27 meters. So that's our given information, right? So we do have some given information in this word problem. So that's what we're going to do. We're going to set up guess method. So for our unknown, that's going to be our arc length. Our equation step is going to come from which formula that combines, let's see what we have. We have radius, we have arc length, and we know our angle. So the formula that combines those, right? If you take a look, arc length, radius, and then your angle. Right? We're not talking about area, so we're definitely going to use this formula. So our arc length is equal to r theta. And then we'll do some substitution. Our arc length is what we're looking for. Our radius is 27. Our theta has to be in terms of radians, unfortunately. So we have our 160 degrees. We have to multiply this by, hopefully you remember, since we have 160 over 1, we want this to be in radians. So we want the 180 degrees in the bottom so that the degrees will cancel out, and we'll be left with our answer in terms of pi. So 160 and 180, right? If you divided each by 10, that would give you 16 over 18. And dividing each of those by 2, right? You would get 8 over 9. So we have 8 pi over 9 radians. Okay, so just double check, right? We divided both of these by 10, so 16 over 18. 16 divided by 2 is going to give us 8, and 18 divided by 2 is going to be 9. So essentially the GCF was 20. All right, and then we just simplify this. It says find the length of the arc intercepted if the central angle is formed. So I guess since this doesn't tell us what to do, we're going to leave it in exact form. So we're going to leave it in terms of pi, but I'll show you how to round as well. So we'll solve this by just simplifying what we have. So we have 27 times 8 pi over 9. This is 27 over 1, so the 27 and the 9 can cancel. 9 becomes 1, 27 becomes 3. 3 times 8 is 24. So our arc length is 24 pi meters. If we want to figure out what that is without the pi involved, right? So this is our exact answer. To round that, we would just take 24 and multiply it by pi. And we'll get 75, right? So if we round it to the nearest tenth, it would be 75.4, right? So this is approximately 75.4 meters of walking. And that finishes example 1. Example 2. A stationary sprinkler sprays water over a distance of 40 feet. So we have a sprinkler, and it's spraying water over a distance of 40 feet. Right? So here's our stationary sprinkler. It sprays water 40 feet away from where it started. And then it rotates through an angle of 80 degrees. So not quite 90. So it's going to rotate 80 degrees. So that gives us what we call this a sector of space, right? Find the area of the ground watered by the sprinkler. So that means the sprinkler is going to rotate, right, and water all of this ground. We're only watering this space. Right, so we're going to use the area of a sector formula for this one. It's nice, this organizes our given information, right? Our given information here, we have 40 feet as our radius. If we were looking for the area, we know that the central angle here, right, is going to be 80 degrees. So theta is equal to 80 degrees. I don't know if you can see that well enough. And that's all that we know, right? So if we're looking at our area formula for area of a sector, we either can use this one if we know the radius and theta, or we can use this one if we know the radius and the arc length. We do not know the arc length, so we cannot use this formula. We can only use this formula. So we're going to use, for our equation, 1/2 r squared theta. And again, this only works if theta is in terms of radians, right? This formula says right here, it's gotta be in radians. So we're just gonna have to do some conversions again, which is fine. This is nice and divisible. Our unknown piece, right? We don't really know the area, right? That's our unknown area of the sector. So we can say that that is equal to A. So A is equal to what we have here. We'll do some substitution. 1/2 our radius squared. Remember order of operations. So we can't do 1/2 of 40 and then square it. And then our theta. So off to the side, we're going to have to convert 80 degrees into radians. We'll multiply this by pi over 180 degrees. Well, let's see. 20 goes into 80 4 times. 20 goes into 180 9 times. So we have 4 pi over 9. So that will be our radian measure. That goes here. 4 pi over 9. Don't worry about converting that to a decimal or anything. We're going to actually use this as a fraction to help us simplify. So that's our next step, solving, right? So 40 squared, right, is definitely going to be 1,600, and we have half of that. So if you want now, we can simplify that to be just 800. We still need to multiply that by 4 pi over 9. So it's 800 over 1, right? Multiplied by 4 pi over 9. 9 goes into 800 evenly. No, it does not. Sorry about that. 9 does not go into 800 evenly. So let's see, does that reduce any further? Well, a quick and easy way to do that, if it doesn't reduce, right, goes in this many times. So we'd have 800 times 4, divide that by 9. So we get 355.5 repeating. So in order to write that as a mixed number, what we can do is we can tell the calculator to do that, right? So we go to alpha y equals, and we're going to turn the decimal into a fraction by using that button. So we have 32. So this is definitely not simplifiable any further. That just confirms that for us. Right? So that's how we can leave our exact answer, right? Our area would be square feet. So, right? But that doesn't really make, much sense if you're talking to somebody about area. So let's go ahead and approximate that to the nearest tenth. Right, we'll do 3,200 times pi, and then go ahead and divide that by 9. So we get approximately 1,117, and then that would be our final answer, square feet. So that's approximately the area that's covered in this space here. That's the area of a sector. So that's the problem. So any questions on that, please watch this video again. Slide 31 is important units for reference. So this will help you if you need to do any conversions with some word problems. So that's there for you. Slide 32 shows your homework. So what's due next class, and essentially since I won't be able to check it, you will be checked on this in 2 classes. You're going to do trig 1.1, 52 through 58 even, 61 and 69. Okay, your trig 1.1 formative will be on 2.5. So when I get back, we'll have time to go over everything that's been covered, hear those helpful formulas again. So if you have any questions on these, just watch these videos again, right? Don't leave anything blank for your homework. Just make sure that you try your best, okay? Because I'm going to be checking that you took your notes and that you worked on trying all of the homework questions.